Okay, we'll just take a few minutes to introduce this workshop. It's really a pleasure for me to welcome you here to this live event for the IROS 2020 workshop, Learning Impedance Modulation for Physical Interaction, Insight from Humans and Advances in Robotics. Here you have the organizers. I will go just through the names. I'm Giuseppe on the left here. Then we have Franco Angelini from University of Pisa.
Hi.
Megan Huber from University of Massachusetts in Amherst, Jungku Lee from MIT, and Manolo Garabini from Pisa again. I will go through the speakers of this workshop just to remind you what is the topic of the workshop and the major points that people covered. This is an alphabetical order. We had a talk from Professor Vicky from the University of Pisa, where he reviewed essentially the role of impedance, human impedance, and how this is a very highly variable quantity. And he also demonstrated how only part of this variability is actually intentional by our motor control, let's say. Then he spent some time to discuss different solutions to replicate variable impedance, which can be achieved, as you know, by software, but also by hardware solutions. And then he demonstrated how the impedance in robots can be modulated using an optimization-based method, but also very promising results can be achieved using learning techniques, for example, learning by demonstration. Then we had Professor David Brown. Unfortunately, this talk had some technical issues, and it has been released a few days ago. But I saw that many of you had the chance to look at the video already. If you didn't, you can go to the website of IROS and check the video because it's really interesting. He discussed it there. He started from the concept of improving the capability of humans by using energetically active robots that can support human motion and provide supplementary power, and introduce this new concept of passive systems that can, in the same way, improve the capabilities of humans during their movements, for example, bicycles and ice skates. And this research is very interesting because it's trying to implement this idea on supporting devices for humans and exploring the concept of human-powered compliant actuation. And then we had Professor Etienne Bourdet from Imperial College in London. His talk was related to the way humans can, and of course also robots, can identify and compensate for external disturbing forces, and how humans can face these disturbances by modulating the limb impedance. And his talk was also related to evidences on the capability of humans of exploiting body impedance to improve visual-haptic perception. And then this optimization of the effort and prediction error, which can explain the adaptation of impedance, resulting in a purposeful shaping of this interaction between the robots and the environment. And then we have Professor Hogan from MIT, who talked about muscles. So from the biomechanics of muscles, how the muscle can generate mechanical impedance. And he showed us how this is a key for the stability of the muscle-skeletal system. And also talked about how this is even a problem because at the same point, you cannot have high force with compliant behaviors. But then this comes to the point of the role of kinematic postures and motions as a consequence in the joint space, of course, and how this kinematic posture, how to choose this kinematic posture to exploit low impedance directions. And there is this interesting work on the wrist and the preferred the low impedance direction of movement of the wrist. And this comes to the robotic side because mechanical impedance has been demonstrated that has the compositionality property, and this simplifies the control of complex tasks and able to manage many degrees of freedom. Then we have Professor Zhangke Li. She didn't have the chance to provide us a talk to this workshop, but she should be here to join this discussion today. And we are really happy to hear what's her thought about our topic. Then we have Professor Angel Li, who is professor at the Arizona State University, and in this workshop discussed with us about physical human-robot interaction and how the physical human-robot interaction should take care of this trade-off between stability of the device and the agility. And in this talk, we saw how it is possible to develop a variable damping controller, which was based on the biomechanics, in order to improve this trade-off while reducing the effort of the human during the physical robot interaction. The idea in a nutshell was that when the user was intended to move, they essentially decreased the damping of the robot even to negative values to improve the agility of the overall system, leveraging on the fact that the impedance of the human is able to stabilize the overall system. And of course, when the user intends to stop, the controller can increase the damping to improve the stability of the system. We had Professor Perot from Northwestern University, who talked about the regulation of impedance in tasks that are consistent with the intrinsic mechanic of our body and in tasks that are not. And his results have shown us that our body requires less modulation of muscle activity when the task that we are doing is consistent with our biomechanics and the direction of our characteristic of muscle, the length of the muscles and exerted forces. And of course, in that case, we have less muscle effort, but also the perception of the subjects is interesting because they reported on much easier, reported that the task was much easier than the other case. On the other side, when the task is inconsistent with the mechanics of our body, then we have to face to this effect, and they demonstrated how rapid feedback pathways enable to compensate for these effects. We had also a great talk from Ludovic Righetti from New York University, who talked about the main role of impedance modulation in robotics, again, as a trade-off between the need to reject external disturbances and the unavoidable uncertainty in the contact locations. And he presented two main works. The first one was an impedance planner that in an optimal way trades off between the contact uncertainty and external disturbances that can ultimately increase the robustness of the system. On the other side, he also demonstrated how an explicit encoding of impedance goals within the learning policies of, for example, reinforcement learning approach is a key point to improve the repeatability of the learning and the robustness. And last but not least, we had a talk from Professor Xinbo Yu from University of Science and Technology in Beijing. In his talk, Professor Xinbo Yu talked about visual and force sensing, which can intended as tools that can be combined to enable physical interaction between humans and robots. And he provided us an example of co-carrying tasks between a robot and a human. And in this framework, as he demonstrated, the impedance band control is indeed the major enabling factor to guarantee a stable and efficient interaction. Okay, I'm done with this big summary. I think we can start with this session. I can stop sharing my screen.
Giuseppe?
Yep.
Just a small note. So if you have questions, so if there are any questions, just write them in the chat and we will ask them to the speakers. So please do it. And that's it. I think you missed this part.
No, of course, of course. Okay, I would like to start with a very general and ambitious question, which is essentially we know that humans are able to modulate in a very effective way their mechanical impedance to enhance the interaction with our surrounding world. And we also saw from different talks how many solutions have been proposed to replicate this capability in robots, either via software, but also hardware, it's the same. So at this point, the first question is what are the major challenges that still need to be solved? Of course, on the robotic side and on human side, what is still missing? And I think it would be I would be happy if Professor Hoga could start to discuss this point.
Oh boy, I get put on the spot. Okay, so on the human side, there's no question in my mind, but the biggest problem is measurement. So I really would like to be able to measure, ideally in real time, but just measure in general time varying mechanical impedance. The big problem is like it's a classic measurement problem. As soon as you try to measure the system, you change it. So I think coming up with ideally non-invasive methods to measure impedance, but if not, methods that can manage the complexity of real human movements. I mean, for example, we've been using, in my own work, we've been using Eric's work on shoulder impedance. And as far as I know, that's the only data that's out there. Is that right, Eric? Anyway, so I mean, and that's very helpful, but the data is pretty thin on the ground. So measurement, I think, is a key problem. On the robotic side, I don't claim expertise, but I think the biggest limitation there is actuators. The actuators that we have don't have the torque density or the power density, and if you try to give them that, then you wind up bringing in nonlinearities like backlash, friction, and so on. But others may know more about that, like say David, for example, David Brown.
If I can ask like a follow-up question, like because Neville just mentioned about the actuator is a problem or challenging issue, we've also seen like a lot of works to mimic human muscle actuators, like artificial muscle actuators, something like that. One of the questions we have had, I think I have had, was like, do we really benefit from mimicking like human actuators with the robotic devices? I also wanted to hear some like opinions about pros and cons of such an approach, if anybody has an answer.
Yeah, I might go with this one. So it depends. If we aim to build a robot to understand the human movement better or what humans do, then maybe we benefit from building actuators that are like muscles. But if we aim to build the best robot, then we might not. So really kind of circling back to the previous question. So the question was, what are the limitations? Now it's difficult to tell really kind of difficult to provide a single answer to that. But well, the question could be, what would make an ideal actuator? So what would make a variable stiffness actuator compete with a direct drive actuator? What would make a variable stiffness actuator compete with a series elastic actuator? And currently it seems that all this is task dependent. For some tasks, a direct drive actuator would be better. For other tasks, an actuator that can store energy in a mechanical domain without domain change, like would be better. So that would be my short answer.
I'd like to go back to the first question and just second Neville's suggestion that I think the fundamental problem, at least in understanding human impedance, is measurement, particularly in functional tasks. We do a lot of measurements in the laboratory, but how those translate to the real world, we're still pretty much in the dark about. But I'd say the second question that's really related once you get better measurements is understanding which impedance modulation is purposeful and which is just a byproduct of the fact that you're using your muscles for some other function, such as to generate force or motion. And just disentangling those two things, I think, is a real challenge.
I'd like to echo that and say it's still not clear to me whether impedance modulation is a bug or a feature.
Exactly. I think it's both, depending on the task you're doing.
Depends on the context. Getting back to the robotics question, my understanding, for example, is that at Boston Dynamics with their Atlas robot, what they count on is having very high bandwidth, very low latency torque control. So they basically they have high quality torque actuators and they don't care about impedance, they just optimize. Now, the optimization results in an impedance, but if you had perfect torque control, you can do a lot. So,
yeah, I think about the robotics part actually, although we have developed several types of VR, basically variable impedance actuators, different concepts as well, but I think people are not still using it a lot because I think there is a design has been there, but also not well established control approaches also there, and also people do not see the great benefit. As Neville Hogan said, right, there is very good torque controlled robots can also do the very much highly dynamic movements and so on, right? So I think having this added complexity to make variable impedance actuator, but we do not see clear, really significant benefit overall. I mean, I think people see the task performance has been improved in certain level, but I think this significance is maybe not there. So I think which is a bit of, I think, the bottleneck, I think, which pushes further to use it in the real robotic system, I guess.
So even if we have actuators with very good torque actuators, we still need to define the relationship between force production and displacement, right? That there's no way around. We need to decide what it should be. And to me, it's not so clear in robotics. Why would you want to vary the impedance? So basically the feedback path of what you do, right? Because even if you have a torque controller, either you have a planner that can replan at the control frequency, which I guess is not possible for a full body, or you need to define a feedback mechanism somehow. And you need to decide what this feedback is going to be and why would that change over time. And to me, as long as we don't define this problem properly, it's not clear why would you want to modulate impedance or what it should look like.
Yeah, this is really a good point. Well, at this point, the next question should be, so why we are using impedance control, right?
Are students also allowed to just raise a question?
Yeah, sure.
Everybody's.
Well, this is actually going back to what Professor Hogan mentioned with Boston Dynamics having perfect torque control. I know IHMC is also trying to do torque control with their whole body controller on their humanoids. But even after optimizing those trajectories, they still impose an impedance control on top of it because there are some uncertainties in terms of terrain or the impact forces that you're going to come across. So once you can have these optimized trajectories, but when you're following them, you would still want a compliant system on top of that to account for these uncertainties in terrain or impacts. And that's where impedance control, in my opinion, matters.
If I may, I think Neville knows exactly well why impedance control is important. He is the person who founded it, basically. So, I get the point that I would say beyond what Neville said, yes, measurement is difficult. We don't have measurements yet. It's a difficult thing to measure, by the way, because it's not a physical quantity. It's an operator. Is a differential equation, basically, right? Is a functional operator between spaces. So it's difficult to measure. Then actuators, yes, we do not have perfect actuators, but it is true that if you had a perfect torque source, then it would be no problem to implement any algorithm and change impedance. Possibly some of the devices that have been made with agonistic antagonistic arrangements are made because they allow you to use less than perfect actuators, less than perfect torque sources, which are extremely costly and not available to everybody. And even our muscles are not perfect force generators, and so we have this agonistic antagonism that somehow replaces this perfection. And I still agree with the fact that we do not really know deeply what are the applications where impedance control is a winner, or soft robotics, if you want. I still remember those papers in the 80s by Eppinger, I think, Warren Searing and Eppinger, that showed very clearly, with a very simple argument, with Rode-Locus argument, and Evie, you probably recall that too, that for doing force control, a rigid robot is much better, even for doing force control, because the authority of the controller is higher. So from a classical standpoint, for classical control, a rigid is better to do even force control, which we would not expect, even in front of uncertainties. Force control is better with a rigid transmission, because you have less delay between the input and the output, and therefore you can compensate it better. Then we had the advent of series elastic actuators, with the idea that having compliance in the transmission could help interact more safely with the environment. But I must say that trying to make that intuition something precise, to write that down in terms of an optimal control problem or anything very analytic has eluded many. I never saw a convincing argument why that is should be better to control something with an elasticity in between the actuator source or the torque source and the motion. Unless you make input into the equation the fact that you want to minimize maximize the resilience, let's say, minimize the effect that external disturbances have on the model. That is definitely a point where you see the difference. If you have compliance, then you can absorb impacts with the environment in a better way than if you don't. Except for that, it's difficult to see in the active role that compliance helps your control. I'm saying this in very elementary terms, right? Like Rode-Locus arguments or stuff like that. So, but we all also have this idea, and basically everybody here, I think, is convinced that impedance is important. And when you change impedance, maybe we don't always use our muscle system to change the impedance voluntarily. Maybe that, as Eric said, sometimes or more often we change our stiffness, muscle stiffness for other reasons, because we exert forces, for instance. But we do change the configuration of our arms. If we want to be stiff, we will push like this, and if we want to be compliant, we push like this. And this is intentionally changing the impedance in this direction, I would say. So we do change impedance, of course, but it is true that it's still a very challenging thing to do, to try to understand what is the right thing to do.
I think it's also important to realize that, you know, no matter what kind of actuator you have or what kind of feedback you have, there's this little detail of remaining stable when coupled or uncoupled from other objects. And one of the strong theoretical reasons to think in terms of impedance is because if you can enforce energetically passive impedance, it gives you a very robust stability in contact with a very wide range of objects. So I think that's, even if we have very good planning, you got to think about the robustness to contact.